Section 6.2. Packaging Spring Boot Applications as Container Images. In the previous chapters, we built the Catalog Service application featuring a REST API and database integration. In this section, as an intermediate step before deploying it to Kubernetes, we'll build an image to run Catalog Service as a container on Docker. First, I'll review some aspects you should consider when packaging a Spring Boot application as a container image. Then I'll show you how to do that with a Docker file and with cloud-native build packs. Section 6.2.1. Preparing Spring Boot for Containerization. Packaging a Spring Boot application as a container image means that the application will run in an isolated context, including computational resources and network. Two main questions may arise from this isolation. How can you reach the application through the network? How can you make it interact with other containers? We'll look at those two issues next. Exposing application services through port forwarding. In Chapter 2, when you ran Catalog Service as a container, you mapped port 8080, on which the application exposed its services, to port 8080 on your local machine. After doing that, you could use the application by visiting localhost 8080. What you did there is called port forwarding or port mapping or port publishing, and it's used to make your containerized application accessible from the outside world. By default, containers join an isolated network inside the Docker host. If you want to access any container from your local network, you must explicitly configure the port mapping. For example, when you ran the Catalog Service application, you specified the mapping as an argument to the Docker run command. P8080, 8080, where the first is the external port and the second is the container port. Figure 6.8 illustrates how this works.
Figure 6.8. Port mapping lets you access the services exposed by a containerized application by forwarding the traffic from the container network to the outside world.
Using Docker's built-in DNS server for service discovery. Thanks to port forwarding, the Catalog Service application in the previous chapter could access the PostgreSQL database server through the URL JDBC PostgreSQL localhost 5432, even if it was running inside a container. The interaction is shown in Figure 6.9. When running Catalog Service as a container, however, you will not be able to do that anymore, since localhost would represent the inside of your container and not your local machine. How can you solve this problem?
Figure 6.9. The Catalog Service application can interact with the PostgreSQL container thanks to the port mapping, making the database accessible from the outside world.
Docker has a built-in DNS server that can enable containers in the same network to find each other using the container name rather than a host name or an IP address. For example, Catalog Service will be able to call the PostgreSQL server through the URL JDBC PostgreSQL/Polar Postgres 5432, where Polar Postgres is the container name. Figure 6.10 shows how it works. Later in the chapter, you'll see how to achieve this result in code.
Figure 6.10. The Catalog Service container can directly interact with the PostgreSQL container because they are both on the same Docker network.
So before moving on, let's create a network inside which Catalog Service and PostgreSQL can talk to each other using the container name instead of an IP address or a host name. You can run this command from any terminal window.
See this code.
Next, verify that the network has been successfully created.
See this code.
You can then start a PostgreSQL container, specifying that it should be part of the catalog network you just created. Using the --net argument ensures the container will join the specified network and rely on the Docker built-in DNS server.
See this code?
If the command fails, you might have the PostgreSQL container from Chapter 5 still running. Remove it with docker rm-fv polar postgres and run the previous command again. Section 6.2.2. Containerizing Spring Boot with Docker files. Cloud-native applications are self-contained. Spring Boot lets you package your applications as standalone jars, including everything they need to run except the runtime environment. That makes the containerization very straightforward, since all you need in a container image besides the jar artifact is an operating system and a JRE. This section will show you how to containerize the catalog service application using a Docker file. First, you need to identify which image you want to base yours on. You could choose an Ubuntu image, as we did before, and then explicitly install the JRE, or you could choose a base image that provides a JRE already, which is more convenient. All the major OpenJDK distributions have a related image available on Docker Hub. Feel free to choose the one you prefer. In this example, I'll be using Eclipse Temurin 17, which is the same OpenJDK distribution I've been using locally so far. Then you need to copy the jar file of catalog service into the image itself. Finally, declare that the entry point for the container execution is the command to run the application on the JRE. Open your catalog service project, catalog service, and create an empty file called Docker file, with no extension, in the root folder. That file will contain the recipe for containerizing your application.
Listing 6.2. Docker file for describing the catalog service image.
This Docker file declares a jar_file argument that can be specified when creating the image with the Docker build command. Before moving on, you need to build the jar artifact for the catalog service application. Open a terminal window and navigate to the catalog service project's root folder. First, build the jar artifact.
See this code?
By default, the Dockerfile script will copy the application's jar file from the location path used by Gradle, build/lib/. So if you're using Gradle, you can build the container image by running this command.
See this code?
If you're using Maven, you can specify the location used by Maven as a build argument with the following command. Don't forget the final dot.
See this code?
In either case, you'll end up with your catalog service application packaged as a container image. Since we haven't specified any version, the image will be tagged as latest automatically. Let's verify that it works. Remember the two aspects I covered in the previous section: port forwarding and using the Docker built-in DNS server. You can handle them by adding two arguments to the Docker run command. -p9001:9001 will map port 9001 inside the container, where the catalog service is exposing its services, to port 9001 on your local host. --net catalog network will connect the catalog service container to the catalog network you previously created so that it can contact the PostgreSQL container. That is still not enough. In the previous chapter, we set the spring.datasource.url property for catalog service to JDBC PostgreSQL localhost 5432/polardb_catalog. Since it points to localhost, it will not work from within a container. You already know how to configure a Spring Boot application from the outside without having to recompile it, right? An environment variable will do. We need to overwrite the spring.datasource.url property and specify the same URL, replacing localhost with the PostgreSQL container name, Polar Postgres. Using another environment variable, we can also enable the test data Spring profile to trigger the creation of test data in the catalog.
See this code?
That's quite a long command, isn't it? You won't use the Docker CLI for long, though, I promise. Later in the chapter, I'll introduce Docker Compose. Open a terminal window, call the application, and verify that it works correctly, as it did in Chapter 5.
See this code?
When you're done, remember to delete both containers.
See this code?
The approach you've just followed is perfectly fine for experimenting with Docker in your development environment and understanding how images work. But you'll need to consider several aspects before achieving a production-grade image. That's the topic of the next section. Section 6.2.3, Building Container Images for Production. Getting started with Docker files might not be that difficult at the beginning, but building production-grade images can be challenging. In this section, you'll see how to improve the image you built in the previous section. You'll use the layered jar feature provided by Spring Boot to build more efficient images. Then you'll consider essential security aspects related to container images. Finally, I'll discuss some factors to consider when choosing between Docker files and cloud-native build packs for containerizing applications. Performance. When building container images, you should consider performance at build time and at runtime. The layered architecture characterizing OCI images enables the caching and reusing of unchanged layers when building an image. Container registries store images by layers, so that when you pull a new version, only the changed layers are downloaded. That is quite an advantage in a cloud environment, considering the time and bandwidth you'll save for all your application instances. In the previous section, you copied the catalog service standalone jar file into a layer in the image. As a result, whenever you change something in your application, the whole layer must be rebuilt. Consider the scenario where you just add a new REST endpoint to your application. Even if all the Spring libraries and dependencies are unchanged, and the only difference is in your own code, you must rebuild the whole layer since everything is together. We can do better, and Spring Boot can help us. Putting Uber jars inside a container image has never been efficient. A jar artifact is a compressed archive containing all the dependencies, classes, and resources used by the application. All those files are organized in folders and subfolders within the jar. We could expand standard jar artifacts and put each folder on a different container image level. Starting with version 2.3, Spring Boot made that even more efficient by introducing a new way of packaging applications as jar artifacts, the layered jar mode. And since Spring Boot 2.4, that's been the default mode, so you don't need any extra configuration to use the new functionality. Applications packaged using the layered jar mode are made up of layers, similar to how container images work. This new feature is excellent for building more efficient images. When using the new jar packaging, we can expand the jar artifact and then create a different image layer for each jar layer. The goal is to have your own classes, which change more frequently, on a separate layer from the project dependencies, which change less frequently. By default, Spring Boot applications are packaged as jar artifacts made up of the following layers, starting from the lowest. Dependencies, for all the main dependencies added to the project. Spring Bootloader, for the classes used by the Spring Bootloader component. Snapshot dependencies, for all the snapshot dependencies. Application, for your application classes and resources. If you consider the previous scenario where you added a new REST endpoint to an existing application, only the application layer must be built when you containerize it. Moreover, when you upgrade the application in production, only that new layer must be downloaded to the nodes where the container is running, making the upgrade faster and cheaper, especially on cloud platforms, which bill for the bandwidth used. Let's update the previous Docker file to containerize catalog service more efficiently using the layered jar mode. Using this new strategy means doing some preparation work to copy the jar file into the image and expand it into the 4 layers described previously. We don't want to keep the original jar file inside the image, or our optimization plan will not work. Docker provides a solution for that: multi-stage builds. We'll divide the work into 2 stages. In the first stage, we extract the layers from the jar file. The second stage is where we place each jar layer into a separate image layer. In the end, the result of the first stage is discarded, including the original jar file, while the second stage will produce the final container image.
Listing 6.3. More efficient Docker file to build a catalog service image.
Note: what if you want to change the configuration for the layers in the jar file? As always, Spring Boot provides sensible defaults, but you can customize it and adapt it to your needs. Perhaps your project has internal shared dependencies you might want to place in a separate layer, since they change more often than third-party dependencies. You can do that through the Spring Boot Gradle or Maven plugin. For more information, refer to the Spring Boot documentation at this link. The process for building and running the container is the same as before, but now the image is more efficient and is optimized at build and execution time. However, it's still not ready for production. What about security? That's the topic of the next section. Security. Security is a critical aspect that is too often underestimated by people getting started with Docker and containerization. You should be aware that containers run using the root user by default, potentially letting them get root access to the Docker host. You can mitigate the risk by creating a non-privileged user and using it to run the entry point process defined in the Docker file, following the principle of least privilege. Consider the Docker file you wrote for catalog service. You can improve it by adding new steps to create a new non-root user that will run the application.
Listing 6.4. More secure Docker file to build a catalog service image.
As previously noted, you should never store secrets like passwords or keys in a container image. Even if they are removed in an upper layer, they will remain intact in the original layer and be easily accessible. Finally, it's also critical to use up-to-date base images and libraries in your Docker file. Scanning your container images for vulnerabilities is a best practice that should be embraced and automated in your deployment pipeline. In Chapter 3, you learned how to use Gripe to scan codebases for vulnerabilities. Now we'll also use it to scan a container image. Using the updated Docker file, build a new container image for Catalog Service. Open a terminal window, navigate to the Catalog Service root folder, and run this command. Don't forget the final dot.
See this code?
Next, use Gripe to check if the newly created image contains any vulnerabilities.
See this code?
Have you found any high-severity vulnerabilities? Discussing supply chain security and related risk management is out of scope for this book. I want to show you how to perform and automate vulnerability scanning for application artifacts, but I'll leave it up to you to follow up on the scan results. I can't stress enough how important it is to define a security strategy in your organization and automate, as much as possible, its compliance verification throughout the whole value stream. In this section, I mentioned a few essential aspects you should consider when building production-grade container images, but there's even more to cover. Is there another way to build production-grade container images? The following section introduces a different option. Docker files or build packs. Docker files are very powerful, and they give you complete fine-grained control over the result. However, they require extra care and maintenance and can lead to several challenges in your value stream. As a developer, you might not want to deal with all the performance and security concerns we've discussed. You might prefer to focus on the application code instead. After all, one reason to move to the cloud is to deliver value to customers faster. Adding the Docker file step and considering all those issues might not be for you. As an operator, it might be challenging to control and secure the supply chain within the organization when container images are built from a Docker file. It's pretty common to invest some time in scripting the perfect Docker file and to copy that into multiple repositories for different applications. But it's hard to keep all teams on the same page, verify adherence to the approved Docker file, synchronize any changes throughout the organization, and understand who is responsible for what. Cloud-native build packs provide a different approach, focusing on consistency, security, performance, and governance. As a developer, you get a tool that automatically builds a production-ready OCI image from your application source code without having to write a Docker file. As an operator, you get a tool that defines, controls, and secures application artifacts within the entire organization. Ultimately, the decision to use a Docker file or a tool like build packs depends on your organization and requirements. Both approaches are valid and are used in production. In general, my recommendation is to use build packs unless it makes sense not to. Note: another option for packaging Java applications as container images without writing a Docker file is using Jib, a Gradle and Maven plugin developed by Google. See this link. In the next section and the rest of the book, we'll use cloud-native build packs rather than Docker files. It was important for me to show you how a Docker file works, because it makes understanding the container image features and layers easier. Furthermore, I wanted to show you how to write a basic Docker file for containerizing a Spring Boot application to highlight what's needed and illustrate the execution of the application jar from within the container. Finally, it will be easier for you to debug containers when something goes wrong, even if they're automatically generated by build packs, because you now know how to build images from scratch. If you'd like to learn more about Docker files for Spring Boot applications, I recommend you look at the official documentation. See this link. Section 6.2.4, Containerizing Spring Boot with Cloud-Native Build Packs. Cloud-Native Build Packs, buildpacks.io, is a project hosted by the CNCF to transform your application source code into images that can run on any cloud. When introducing containers in Chapter 1, I underlined how PaaS platforms like Heroku and Cloud Foundry are actually using containers behind the scenes, converting your application source code into containers before running them. Build Packs is the tool they use to accomplish that. Cloud-native Build Packs has been developed and advanced based on Heroku and Pivotal's many years of experience running cloud-native applications as containers on their PaaS platforms. It's a mature project, And since Spring Boot 2.3, it has been integrated natively in the Spring Boot plugin for both Gradle and Maven, so you're not required to install the dedicated BuildPacks CLI pack. These are some of its features. It auto-detects the type of application and packages it without requiring a Docker file. It supports multiple languages and platforms. It's highly performant through caching and layering. It guarantees reproducible builds. It relies on best practices in terms of security. It produces production-grade images. It supports building native images using GraalVM. Note: if you'd like to know more about Cloud Native Build Packs, I recommend watching Cloud Native Build Packs with Emily Casey. See this link. Emily Casey is a member of the Build Packs core team. The container generation process is orchestrated by a builder image containing the complete information on how to containerize your application. Such information is provided as a sequence of build packs, each dedicated to a specific aspect of the application, such as the operating system, OpenJDK, and JVM configuration. The Spring Boot plugin adopts the Paketo Build Packs Builder, an implementation of the Cloud Native Build Packs specification that provides support for many types of applications, including Java and Spring Boot ones, Paketo.io. The Paketo Builder component relies on a series of default build packs for the actual build operation. This structure is highly modular and customizable. You can add new build packs to the sequence, for example, to add a monitoring agent to the application, replace existing ones, for example, to replace the default Bellsoft Liberica OpenJDK with Microsoft OpenJDK, or even use a different builder image entirely. Note: the Cloud Native Build Packs project manages a registry where you can discover and analyze build packs you can use to containerize your applications, including all the build packs from the Paketo implementation, registry.buildpacks.io. The BuildPacks integration provided by the Spring Boot plugin can be configured in the build.gradle file located in your catalog service project. Let's configure the image name and define which Java version to use through an environment variable.
Listing 6.5, Configuration for Containerizing Catalog Service.
Go ahead and build the image by running the following command.
See this code?
Warning: at the time of writing, the Paketo project is working on adding support for ARM64 images. You can follow the feature's progress on the Paketo BuildPacks project on GitHub. See this link. Until it's complete, you can still use BuildPacks to build containers and run them via Docker Desktop on Apple Silicon computers. However, the build process and the application startup phase will be slower than usual. Until official support is added, you can alternatively use the following command, pointing to an experimental version of Paketo BuildPacks with ARM64 support, /gradlew bootbuildimage -- builder. This link. Be aware that it's experimental and not ready for production. For more information, you can refer to the documentation on GitHub, this link. The first time you run the task, it will take a minute to download the packages used by BuildPacks to create the container image. The second time, it will take only a few seconds. If you look closely at the output of the command, you can see all the steps performed by BuildPacks to generate the image. These steps include adding a JRE and using the layered jar built by Spring Boot. The plugin accepts more properties to customize its behavior, such as providing your own builder component instead of Paketo's. Check the official documentation for the complete list of configuration options. See this link. Let's try running Catalog Service as a container once again, but this time we'll use the image generated by BuildPacks. Remember to start the PostgreSQL container first, following the instructions in section 6.2.1.
See this code?
Warning: if you're running the container on an Apple Silicon computer, the previous command might return a message like, "Warning, the requested images platform, Linux/AMD64, does not match the detected host platform, Linux/ARM64/V8, and no specific platform was requested." In that case, you'll need to include this additional argument to the previous command, before the image name, until support for ARM64 is added to Paketo BuildPacks, --platform Linux/AMD64. Open a browser window, call the application on localhost 9001 books, and verify that it works correctly. When you're done, remember to delete both the PostgreSQL and catalog service containers.
See this code?
Finally, you can remove the network you use to make catalog service communicate with PostgreSQL. You won't need it anymore after I introduce Docker Compose in the next section.
See this code?
Since Spring Boot 2.4, you can also configure the Spring Boot plugin to publish the image directly to a container registry. To do so, you first need to add configuration for authenticating with the specific container registry in the build.gradle file.
Listing 6.6. Configuration for containerizing catalog service.
The details on how to authenticate with the container registry are externalized as Gradle properties, both for flexibility. You can publish the image to different registries without changing the Gradle build. And for security, the token in particular should never be included in version control. Remember this golden rule of credentials: you should never give your password away. Never. If you need to delegate some service to access a resource on your behalf, you should rely on an access token. The Spring Boot plugin lets you use a password to authenticate with the registry, but you should use a token instead. In section 6.1.3, you generated a personal access token in GitHub to let you push images to the GitHub container registry from your local environment. If you don't know its value anymore, feel free to generate a new one following the procedure I explained earlier in the chapter. Finally, you can build and publish the image by running the boot build image task. With the --image name argument, you can define a fully qualified image name as container registries require. With the --publish image argument, you can instruct the Spring Boot plugin to push the image to the container registry directly. Also, remember to pass values for the container registry via the Gradle properties.
See this code?
Tip: if you're working on ARM64 machines, such as Apple Silicon computers, you can add the --builder ghcr.io/thomasvital/java builder ARM64 argument to the previous command to use an experimental version of Paquito build packs with ARM64 support. Be aware that it's experimental and not ready for production. For more information, you can refer to the documentation on GitHub. See this link. Without this workaround, until official support is added, see this link, you can still use build packs to build containers and run them via Docker Desktop on Apple Silicon computers. But the build process and application startup phase will be slower than usual. Once the command completes successfully, go to your GitHub account, navigate to your profile page, and enter the Packages section. You should see a new catalog service entry. By default, packages hosting container images are private, similar to what you saw with the MyJava image you published in section 6.1.3. If you click on the catalog service entry, you'll find this image you just published, Figure 6.11.
Figure 6.11. Images published to the GitHub container registry are organized as packages.
However, the catalog service package is not linked to your catalog service source code repository yet. Later, I'll show you how to automate building and publishing your images with GitHub Actions, which makes it possible to publish images in the context of the source code repository from which they are built. For now, let's remove the catalog service package that was created when you published the image so that it won't cause any conflicts once you start using GitHub Actions to publish images. From the catalog service package page, Figure 6.11, click Package Settings in the sidebar menu, scroll to the bottom of the settings page, and click Delete this package, Figure 6.12.
Figure 6.12. Delete the catalog service package created manually.
Note: so far, we've been using the implicit latest tag for naming container images. That's not recommended for production scenarios. In Chapter 15, you'll see how to handle versions when releasing your applications. Until then, we'll rely on the implicit latest tag.